welcome back, everybody. Before I get started, does anybody have any questions from the last session they wanted me to cover? Yeah.
So this discount parameter?
Yes, discount factor.
Yeah, the discount. So it makes all the later actions have smaller rewards. But many times in games, like what you showed us, you only care about the final action that brings you the victory. It seems like this kind of thing won't give you anything for games where there are thousands of steps, and this parameter will be close to zero. Okay.
Well, so it's a great question. And the question was, what about things like games where you might only have one reward, like you win or lose, and it's really, really far out? So in principle, that doesn't matter. If that's the only reward signal, it doesn't matter if it's gamma to the 100. It'll still be better to win rather than to lose. So that's fine. But if you generally have a problem where you know there's going to be a finite end, like with probability 1, you're going to have a finite horizon when it terminates, then you can extend everything we're doing here to that case. So for simplicity, for most of the math, I'm not going to do that during the next few lectures, but it's fine to just make it so that h is a random variable. And as long as with probability 1, you terminate, then your value function is still bounded. So let's say you just get a 1 if you win the game of Go, or you get a 0 otherwise, and you know that games are finite in length because the board can only fit so many pieces, then it's fine just to allow h to be a finite horizon, that just meaning when the game ends, and your reward will just be 0 or 1 in that case. And the big challenge is the credit assignment problem, which is that the steps that you took in order to achieve that win or losing, you have to figure out which actions are associated or credited with that future success. Any other questions? All right, let's keep going. So right now what we're going to first talk about is we're continuing to be in the tabular setting. We just have a lookup table for our value function. Someone's given us the Markov decision process, which means that we have a state, an action, a dynamics model, and a reward function. What we talked about before was value iteration, which was one way to compute the optimal value function, or expected discounted sum of rewards, which is maximal. I'm going to talk now briefly about policy search and policy iteration. I'm going to talk about this in particular because it's a very popular, it's sort of a groundwork for a very popular approach now with deep reinforcement learning. And it also will start to be very helpful when we talk about the situation where we don't know the dynamics model and we don't know the reward model, which is the general case for reinforcement learning. So in this case, if we're doing policy search, if we have a finite set of states and actions, then the space of possible policies, that's deterministic mappings from actions to states to actions, is a to the s. Now, if you have non-deterministic policies, you can have an infinite policy class. But if it's deterministic, it's finite, and it's a to the s, so it's exponential in the state space. And you could enumerate them all and compute the value of them separately, but that can be very computationally challenging. So better than that is policy iteration. So what is policy iteration? Policy iteration is going to look a little bit related to value iteration. The goal of policy iteration is, again, so the goal is to compute V star and pi star. So it's the same goal as what we had before, given our MDP. And in value iteration, what we saw is that we always had the optimal value as if we only got to make a finite number of more decisions. So we first computed it for if we could make 1 decision or 0 decisions, and then 1 decision, and we kept kind of backing up. So we always had an optimal value function, but for sort of only a finite number of steps. Policy iteration is going to take a different approach. At any given time, you're going to have a policy that tells you how to act forever, and you're going to compute the value of what that policy is, as if you were to follow it forever. It just might not be a very good policy. So we're always going to have a complete policy that tells us how to act for all our states and actions. And what we're going to do is we're going to first evaluate how good that policy is. So we're going to compute its value. It's its expected discounted sum of rewards. And I'll talk in a second about how we do that. And then we're going to improve it. And so in order for this to converge, we're going to need a couple things. We're going to need the fact that the policy space is finite, which it is in this case. And the second is that we don't repeat policies. There can't be a loop. And if we can guarantee that, like if we can guarantee monotonic improvement, then we'll be guaranteed that this will converge. And it'll converge in at most a to the s iterations because there's only a to the s policies. Okay. So how do we do this? Well, the first thing is, so we're going to start off with a policy here. We can initialize it randomly or in other ways. Computationally, this makes a difference. In terms of convergence, it does not. So the first thing we want to do is evaluate how good a policy is. One way we could do that is by taking the same algorithm we talked about before for value iteration, and instead of having that max operator, we can fix what the policy is. So we can take a sort of a modified Bellman. So what would this look like? That would say the value pi of an s is equal to the reward of s and pi of s. So now we're not allowing ourselves to choose any action. We're fixed to the policy we're evaluating, plus gamma sum over s prime, probability of s prime given sa, v pi of s prime. So we could use sort of a modified value iteration approach here. And just like what we did with value iteration, you can kind of see it underneath here. Instead of having that max a, we would fix that a to be pi of s. And we would do this over and over again until convergence. And that would give us a policy. And then the next step is policy improvement. Now, policy improvement can be done in various ways. But actually, before I get there, I'll say one other thing. So this is one thing you could do, this kind of dynamic programming backup approach. If you're in a finite state and action space, you can do this analytically because this equation no longer involves a max, so it's a linear equation. So the alternative to doing kind of an iteration approach is that we can write this down in vector form. And this is equal to reward per pi. So if you think about your reward as being a matrix of states and actions, if you select the row, if you select the columns that are associated with the policy that you're following, that gives you a reward vector. So you can write it in matrix form like this. And I'll write this. This is the transition model that's associated with only the entries for taking the action that follow the current policy. So if we write it in matrix form, we get something that looks like this. Notice there's no maxes. And you can just invert this. You can just get a matrix inverse. So it's generally an S cubed operation or S 2 point something operation. So it's a little bit expensive in the size of the state space, but you can just analytically solve for this. So this is the analytic solution. So we can either solve for v pi iteratively using dynamic programming, or we can solve for it analytically. But then the challenge is how we do policy improvement. Yeah?
Why can't we do the analytic solution? In which case?
You can do it here because it's tabular, like you only have a finite number of states and actions. And so you can think of this as a matrix. So what I can give you an illustration. So this would just be, you can think of this as the probability of S1 given S1 pi of S1. I'll use that to make it a little bit larger. Okay. So this is like, remember our dynamics model says the probability of ending up in this state given you take a particular action for all of the actions, but if you are constrained to only take one action for each state, then this just becomes a matrix. It's an S by S matrix. So this is an S by S matrix. This is an S-dimensional vector. This is an S-dimensional vector, and you can just solve. The challenge generally is the max part of the operator. This is now just a set of linear equations. Okay. And again, because gamma is going to be less than 1 in this case, and so everything will be fine in terms of singularity. Okay, so these are two different ways that we could compute the value of the policy, given that we know the dynamics model and the reward model. But now we want to do policy improvement. That just tells us what the value is of the current policy, and what we want to do is now get a better policy, because our assumption is that however we randomly initialize the policy is probably not very good, and we want to get to that pi star and v star. Okay. So to do this, let's talk about a slightly different definition, which is the Q value. And the Q value is very much like V, except for it says, for a particular policy, what would be the value if I started off and took the action A, and then from then onwards followed policy pi. So it's like someone gives you a policy, and you first get to pick a particular action A, and then afterwards, for all time steps, you're going to follow the policy pi. So it's RSA plus gamma, discounted sum of future rewards from following that policy. So if we have the computation of a policy and we want to know what its Q value is, then for each state action pair, we're going to compute the RSA plus this discounted sum of future awards from policy pi I. Remember, in the policy evaluation stage, we just computed this. So we have that. This is known. This is known because this is just part of the definition of the MDP. So this allows us to compute the Q pi by doing this for all S and A. And so then if we want to do a step of policy improvement, then we can just be greedy with respect to the Q value. So what this Q value tells us is it says, what is the expected discounted sum of future awards if you take this action and then follow policy pi? And now I'm going to say, I want to compute a new policy, pi I plus 1, which is greedy with respect to that, we often say. So this would be called greedy with respect to Q pi I. And that's going to be our policy improvement step. And what I'm going to argue to you is that by doing this, we're going to get monotonic improvement. So what we would like to say is that V pi I plus 1 is going to always be greater than V pi I. And that's what's going to make policy iteration a sound approach, and one that's guaranteed to converge. Okay. So this is what policy iteration now looks like. We're going to do this MDP value function evaluation, and then we're going to compute Q, and then we're going to do policy improvement. Now, I want to highlight here that there's something a little bit subtle that's going on when we do this step, and that's for the following. So let's look at what we're doing in this case. Q pi I is, again, this immediate reward of taking action A plus the discounted sum of following pi I from then onwards. So what we're going to then do is we're going to take sort of a max over A, which is going to be guaranteed to be greater than or equal to the reward for the previous policy. Right? So this is a max over the actions, and policy pi I was taking a particular action, so if we take a max, that's always going to be strictly greater than or equal to that. And so this was equal to our previous policy value. So the thing that is a little bit subtle, and I think I will skip it for now, just so that in the interest of time, though I'm happy to talk about it afterwards, is that this is a little bit weird, right? Because what we're going to do is we're going to get this new policy that is, in fact, not going to just take that action once and then follow pi I from then onwards. So what does this statement say? This says that if you were to take this new action and then follow pi I from then onwards, then you would be guaranteed to be at least as good as the value of your old policy. But this is not what we're going to do. What we're going to do is we're going to compute this new policy, and we're always following this new policy. And so a priori, it should not seem obvious that that's necessarily going to be a better value function, because we're not going to follow the old policy on the remaining time steps. So that's slightly subtle. And so I encourage you as an exercise to do that proof to show that, in fact, this is monotonically improving. So if we follow this new updated policy, it is in fact guaranteed to be a monotonic improvement compared to the old policy unless we're at pi star. So this is if pi I plus 1 is equal to pi star is equal to pi I, then we halt. And the nice thing is, because of this monotonic guarantee, the only time the policy will not change is when we're at the optimal policy. And since there's a finite number of policies, so the total number of policies is A to the S. So the number of times we have to do this improvement is at most A to the S. Okay, so could we take the screen up, please? So That's going to conclude our very, very brief introduction to how to do planning and compute an optimal value function and policy given models of how the MDP works. And what we're going to now start to do is think about how we can do this when we're not given an MDP reward and dynamics model. So we're going to still assume that we know that there's a state space and there's an action space, and we know what the discount factor is. But now we're going to assume that we don't know. So we're now in the RL case, where R and T are unknown and can only be observed through samples. So we only get to experience a next state if we take an action and a state and transition. So this is, again, be a little bit more similar to the bandit case that Kevin talked about, because things are censored. We only get to observe a reward, and in our case, too, a next state, if we actually take an action in a state. And then we get to observe a reward in the next state. And so now we're going to want to be able to have a similar goal of wanting to find V star and pi star in these settings where we don't know how the world works. And so I think for this case, it's useful to start by thinking about how do we do evaluation, meaning that how do we just simply compute the value of a particular policy, and then once we can do that, we'll do control. So I'll just rewrite out sort of what those definitions are. So we're going to start by doing policy evaluation, which we just talked about for policy iteration, which means that someone gives us, given pi, compute v pi or q pi. But now without access to the reward function or the dynamics model. And then we're going to try to do control, where we want to compute pi star. And we might want to both compute these things, and we might want to start acting according to them, too. So these problems are separate. We can be in a case where we know what the optimal V star is, but we are not following pi star. So it depends exactly what we want to be doing. But we're going to start with policy evaluation and then move to control. So right now we're going to start with, just like in policy iteration, thinking that someone's given us a policy. We can always, we're still all in the tabular setting. We will be for the rest of today. So there's only a finite number of policies. We can just pick any policy we want. Later we'll pick it in a more smart way. And now we just want to compute what the value of it is. Okay, so the first thing that we could do is do Monte Carlo evaluation, which we talked a little bit about before. So Monte Carlo evaluation. And this is only going to work when our horizons are finite. They don't always have to be the same length. We could have different length episodes, but we have to have finite horizons. So we're going to finite horizon. H has to be less than infinity. And then we're going to recall what we talked about before, which is if we think about there being a particular return, so let's call this the ith episode, and the reward for this was R1 plus gamma R2 plus gamma squared R3, where the states and rewards were sampled from the policy that we were following. So we had these returns, which was just if we follow a policy for a particular episode, starting from starting from S0. Again, we can extend all of this to if we have a distribution of starting states, but let's just think about there being a single starting state for right now. So this is one particular return. And in this case, we can do this by just executing in the world. So our agent starts off in a certain state, and then it follows a policy until the episode ends, and then we sum up all the rewards. And so we don't need to know what the dynamics is here. We just need to have our agent experience it. And then our value, like what we talked about before, is that equal to E, where the states are sampled according to our policy, and GT starting from S0. I'll call this GI. So we can do this procedure actually whether we have direct access to the dynamics and reward model or whether we can just sample them from our environment. All right, this is just our expected G. Thanks. This is to index. So this is like this is the ith episode. I was considering whether to put it below, but generally I'm gonna try to mostly use the lowercase for the time step, so the time step within an episode, and then I'll try to use I superscript, not as a power, but to index which episode we're in. Yeah?
And the S is only actions are sounded according to pi in the expectation.
So here, great question. Here, for most of today, unless I say otherwise, I'm going to assume the policy is always deterministic. So we're going to assume that this is going to be a sequence of states where the action is uniquely determined according to the policy. So I'm in a state, I look up in my, my policy just tells me exactly what action to take. All right, so then we just average. Now, one thing that I want to highlight here is that this is not bootstrapping. What do I mean by that? I mean that we're starting in a start state, we just run out to the end of a horizon, we get one return, we reset back to our initial start state, we repeat this, 100 times, or use turn-off Hofting, et cetera, to decide how many samples we need, and we're just going to average all of those, and this is going to concentrate. In contrast, when we looked at the Bellman equation, we were bootstrapping. This is bootstrapping. And this is the same, I'm using the word bootstrapping because if you read the Sutton and Bartow book about reinforcement learning, they use this terminology a lot. So in this case, we're not bootstrapping because we're never substituting in an estimate of the value from future states. We are rolling all the way out to the end of the horizon. We are not able to do an update until we go all the way out to the end of the episode. So if we were doing this in an online case, we'd have to wait till we finished treating the patient. If they had side effects along the way that we considered negative reward, we couldn't update until we finished. And we got the complete return for a whole episode, and then we could update. As we'll see shortly, in things that are more like dynamic programming or in TD methods, temporal difference methods, which we'll get to shortly, we bootstrap in that we can substitute in an approximation for the value of future states, which is often going to be an estimate instead of a perfect value. But Monte Carlo does not do that. It does not have to assume the world is Markov. Oh, yeah.
Should we be pi of S naught then, right?
V pi of S naught, yes. Okay, thank you. Yeah.
For this to be effective, do we need to know that like all of the S0s will get hit if we run this a bunch of times?
Great question. So the question was, for this to be effective, do we need to make sure that any of the S0s will get affected over time? Yes, if you want this to be accurate for all the S0s, we're assuming that you're sampling randomly from S0 or the set of S0s. So asymptotically, that'll be fine. The amount of data you need will depend on sort of what's the minimum probability for any of the S0s to be hit. When we start to get into the control setting, that becomes even more important. Yeah, go ahead. Yeah.
In the policy evaluation setting or the policy improvement part of it, when we do the greedy respect to the value function, so we inherently are assuming that we do have enough exploration because we do have a lot. So we are not going to go through like other. So if we think that greedy is the optimal way to go.
Great questions. Hold that thought for a second. So the question was about exploration and how we're going to do the different state. Right now, we're just in the evaluation case, and when we get to the control, I'll start addressing that. So right now, we're only evaluating. Someone's giving us a policy, and we're just executing. This is not telling us what we're going to do, what we're going to need to do if we have to do control.
So the terminology of control just has to do something with the policy. So it's just the optimal policy. Like What does that?
What does control mean? This case, we're assuming that someone is telling us how to act. They're giving us a policy. Okay? In this case, we're trying to learn how to act. We're trying to learn what the policy is. So right now, it's like your boss tells you, this is the right way to treat, to serve customers' ads. How good is it? How much revenue does it make me? And so then you go off and you run your policy for a month, and you're like, it makes you, $1 billion. Later, they say, okay, well, I'd like you to optimize that, and that's when we'll get into control. And then we're going to have to think about how we trade off between what are the actions we should be taking and what data it gives us.
So then control and policy improvement is the same.
It doesn't have to just be policy improvement, but yes. Yeah, control is generally the full reinforcement learning problem of how do we act in order to optimize reward over time. And we can have different metrics there for how we evaluate success. It's a great question. Okay. All right, so this, let me just highlight a couple other properties of this. So this does not have to assume, does not require Markov assumption. Because all we're doing is we're executing our policy in the world. We don't know how we're getting states. We don't know what the dynamics model is. We don't know what the reward model is. We are assuming stationarity. Someone asked me afterwards. Thanks for reminding me to clarify that. I'm assuming throughout everything that the dynamics model and the reward model are stationary. In real cases, that is almost definitely not the case. For customers, preferences change over time in strange ways, sometimes due to factors that are not controllable by the system. But for everything, almost all of RL assumes that fundamentally you might not be able to observe it, but the dynamics model and the reward model are stationary over the course of trying to learn to make decisions. Okay. So this does not require the Markov assumption, doesn't do any bootstrapping, so no bootstrapping. We're not substituting in an estimate of the value function for later states. And it requires episodic. So if you just have a single trajectory or a single episode, you can't do this because you have to wait till the end. Okay. One thing I want to highlight here in terms of how we evaluate these different approaches for doing estimation is that we often think about it in terms of bias and variance and mean squared error. So this is going to give us an unbiased estimator. This is unbiased, but it's typically high variance. And it converges by the law of large numbers. So it's an unbiased estimator. There's no later, bootstrapping is not causing some potential problems here where it's unbiased, it just might be high variance. You might need a lot of samples for this to converge, but it will converge to the true solution by the law of large numbers. Our estimator, you can think of this as if you are updating this over time, that after each round, you can compute a new update. So let's see, we can do something like this. For I equals 1, ... we can update, can have a v approximate of pi, which is just equal to an average for 1 to I, call this j equals 1 to I of g. So running, it's an average over all the episodes we've seen so far and their returns. And you could be updating this over time. And so in this case, this would give us an estimator that asymptotically will converge to the true value. Thanks for the question. This is one way to write it. Another way to write it is a running average, and we'll talk more about that in a second. Yeah?
The episodic version of it, like why can't we have just one infinite length of a trajectory and then wherever I see S naught, like how, I don't know why
Yeah.
we require episodic.
So you can, okay. So maybe there's two questions in there. One question is whether you can handle just having an infinite trajectory. A second question is whether or not maybe you can do multiple updates if you re-encounter S0. I think you're asking both of those. There is a version of Monte Carlo called every visit, which is every time you encounter S0 or a state you're wanting to estimate, you sum up the reward from that point to the end of the episode. That becomes a biased estimator. It's still asymptotically consistent. The other part of the question, though, I think, is why do you have to wait till the end? You don't always. We'll talk in a second about other estimators which don't require you to wait till the end. The reason here you wait till the end of the episode, and that gives you an unbiased estimator of what is the return. If you don't do that, then we're going to need some approximation to be plugged in of what would be expected discounted sum of rewards starting from that point forward, and you haven't ever observed it. Yeah.
Does the high variance normally comes from the length of this trajectory?
Great question. The high variance typically comes from the variance of the optimal value function. One of the big advances that's happened in the sample complexity of reinforcement learning is trying to bound very tightly how much data we need in order for these things to converge. And it typically, an interesting result that Andrea was responsible for that we published this summer was arguing that it's not just really about the length, it's about the variability in the value function. So you could have a really long value function, but if it's only 1 or 0, like if you're playing a game, then that's not a very high variance, and you might need way less data to try to approximate it. But if you have an enormous amount of range, if your variance is high in the optimal value function, you need a lot of data. And for those of you that are familiar with it, you can sort of see that from Bernstein's inequality. But we generally know our concentration inequality results depend on the variance of the random value. So that's MC policy evaluation. Let's now talk about TD learning. So I'll do it here. So temporal difference learning is an alternative. This is still for evaluation. So we're still going to assume that someone's given us a policy. And this is an alternative that gets at some of the limitations of this that you guys were just bringing up. So this is essentially a combination of Monte Carlo approaches with dynamic programming. The challenge, so why can't we do this? Why can't we just, do the Bellman backup? Well, the challenge is that if we don't have the dynamics model and the reward model, we can't compute this directly. Now, one thing you could imagine doing is taking all your data that you have so far and using machine learning to compute an estimate of the reward function for the data that you have and an estimate of the dynamics model for the data that you have, and then doing Bellman backups with those approximations. That turns out to be a really great idea often, particularly when you're doing theoretical results, and we'll talk a lot about that. The downsides of it, sort of intuitively, is that if you make this into a hat here, if these are empirical estimates, whatever errors you have are going to propagate. But perhaps even more, probably Rich Sutton or someone like that would say the bigger issue is that this is really computationally expensive. This is S squared A. And I think of Rich as often being really concerned with wanting things that are very computationally efficient, so that if we're acting online, we can really quickly leverage our data and then use it to make more decisions quickly and improve them over time. So temporal difference learning is not going to do this. It's called a model-free approach. Model-free. It's a little bit weird notation, perhaps for a machine learning person, because we often will be still assuming some form of parametric model for the value function, particularly when we start getting into function approximation. But it's considered model-free in the sense that we're not estimating a dynamics model and reward model directly. Okay. And what it's going to do is it's going to be sort of kind of combines DP plus MC ideas. And the nice thing is that you can use it in episodic or infinite horizon. And it's going to immediately update the value function after every single state action reward next state tuple. So after every S, A, R, S prime can update V pi. So you're in a state, you take an action, you get a reward, you transition to a next state, you can immediately use that information to improve your estimate. You can immediately improve your estimate. Okay, how does it work? So what we could do is, let me first write sort of what we would see for kind of like a Monte Carlo estimator that is a running average. So let's think of like a Monte Carlo estimator that updates at each S0. So in this case, we could think of it as being V pi of S0 is equal to V pi of S0, whatever our current estimate is, plus alpha gi minus V pi of S0. So what is this doing? This is saying, well, instead of trying to keep all of your data and averaging it over all of the returns you've seen so far, why don't we just, for maybe memory reasons, keep track of our current estimator, and then every time we finish an episode, we slowly move our average a little bit based on the return we just saw. So I have an estimator, I run my policy for an episode, I observe GI, this is my ith episode, and I compare that to my current estimator. That gives me a difference. And I have a constant here between 0 and 1. And I move my estimator over a little bit. And what we're going to do now is that, as we were talking about, this requires us to rate to the end of the episode. But instead of doing that, we could get an approximation for it. And what's an approximation for it? Well, we're going to plug in our estimator. So the idea is we could instead approximate V pi of S prime as the immediate reward plus our current estimator of S prime. Now that's just a sample, because note we've dropped the expected discounted sum of rewards here. So this is sampling, because we're sampling an expectation. We should have done an expectation over all the next states. We're not. We're just sampling one. And we're bootstrapping. So this is the same as Monte Carlo, and this is the same as a DP. So we're sampling this because we only get one next state instead of the full expectation. And that's very similar to what we did here, because we only sampled one trajectory. We didn't get to do the full expectation. And then we plug in our current estimator. Yeah?
Just a little confused with the notation. So the twiddle is our estimate, the twiddle.
Yes.
And then on the right-hand side, is it the hat?
Yeah, sorry, both of these, I can put that here too. These are both our estimators, and we're going to update our estimate.
So on the left, I should think of the left, it's like an update, like a plus or a...
Yeah, it's like an operator. Yeah. Yes. Sorry, dynamic programming. Dynamic programming is what we were doing here. So for the general Bellman operator, it was doing dynamic programming, where we could compute a full expectation over the next state and the value function. In Monte Carlo, we did not do that. We did not do a full expectation over the next state. We just sampled the next state. And now what we're going to do is we're again going to sample a next state, and then instead of rolling all the way out to the end and getting an unbiased estimator of the full expected discounted sum of rewards, we're going to plug in our estimate of what that would be. Yeah.
Is S prime where you go to on applying highest, or just any state?
Oh, this great question. For this tuple. So we're in a state, we took an action, this is going to be pi of S, because we're doing policy evaluation. We observed a reward, and we reached an S prime. So this is sampled, implicitly, this is being sampled from our unknown dynamics model. Great questions. Yeah, so this is an unbiased sample from our dynamics model. This is pi of S. Yeah.
Okay, maybe this is what just got asked, but I'm so confused. So we have V, we're updating V of S prime.
That's right.
So they're all S's, except for the last one?
Yeah. Just like here, right? So for here, when we were doing value iteration, the way we computed the value of a state is we said what was its immediate reward plus gamma times the expected discounts and rewards of the value of the next state. It looks almost identical to that, except for I'm not doing a sum.
Oh, so we know our next state from the data, and so that's what S prime is
That's
being used as? Okay.
That's right, exactly. So we're in the world, we're generating this from our real data experience. We're in a state, we take an action, we observe a reward, and the world gives us the next state. And then we do this update. Thanks.
question. Does this formulation also help us to reduce the variance compared with the trivial Monte Carlo?
Yes, great question. Oh, great. So the question for those of you who couldn't hear in the back is that not only does this allow us to update more quickly, and there's a computational benefit, but can it also reduce the variance? Yes. Okay, because this value function is implicitly trying to approximate the discounted sum of the expected discounted sum of rewards. So we expect this to be biased and a lower variance estimator compared to Monte Carlo. Because V here, so notice before for those G's over there, those were sums over the entire trajectory. And this one, we hope, will often be lower variance. Okay, so the hope is that this is going to be biased. Why is it going to be biased? Because this is an approximation. Okay? This is not really an unbiased sample of the future reward. This is whatever our estimator is, particularly at the beginning when we've, when we set V hat to be 0 everywhere, it's certainly going to be biased. So this is biased, but it's often going to be lower variance. Approximating that. Okay, so let's write down exactly what TD is. This is to kind of give us, this is the idea to move towards this. So the temporal difference learning, which we call TD, is going to look like the following. So we're going to say V pi of S is equal to, and just shout out if I'm mixing notations, plus alpha times R plus gamma V pi. I'll put hats everywhere to remind ourselves that these are all approximations of S prime minus V pi of S. Okay. This is often called the TD target. Okay. So this is saying that once I'm in my state, take an action, observe a reward, and go to the next state, the way I update my current estimate of the value is I take my previous one, and then I shift it over a little bit depending on how different my immediate reward plus gamma times V pi was compared to my current estimate of V pi of S. Okay, and so this is called the TD target because this is sort of the value, our new estimate. This is our new target value. People often call this whole thing the TD error. And you don't need things to be episodic anymore, but it is assuming Markovian structure. So this is, you don't need episodes, do need Markov. Because just like value iteration, we're assuming a Markov structure to do this update. Okay. So this is one thing that I think is an interesting connection for this is that this process is strongly connected to stochastic approximation for why this works. I'm just going to briefly go through not why this converges, but why something close to it or something related to it converges in terms of this process. And that's going to give us insights in terms of how we set this alpha. Because we have to have conditions on alpha in order for this to converge. So I'm going to preview something that's going to look quite a bit different than this, but it'll give us intuition for this part. So let's just think about mean estimation. Just estimating the mean of any variable. Mean estimation. And we have some variable x. X is a random variable, which is in 0, 1. And we're going to say that x0 ... xm is IID values of that x. Of x. And we're going to be trying to compute the mean. And so we're going to define a sequence mu m, where m is in Rn, by the following. This is where it's going to start to look similar. So we're going to say mu m plus 1 is going to equal a weighted sum of our previous estimate of mu plus alpha times our new observation. So this is where it should start to look similar to TD. Yeah. Sure. So this is like our TD estimate. What is, why is this not exactly equivalent? Well, first of all, I'm talking about x's. Second of all, I'm assuming these are all IID. So, but let's go through this to give us some intuition for the TD setting. So this is our definition for how we're going to update our estimate of the mean of the x's. And we're going to assume that our first estimate was just equal to our first sample. Okay. So what the theorem says, yes. Theorem tries, oh look, lovely. Okay, so what the theorem says is that if alpha m is in 0, 1, such that the sum over m greater than or equal to 0 of alpha m is equal to infinity, positive infinity, and the sum over m greater than or equal to 0 of alpha m squared is less than positive infinity, then um is going to go almost surely to the expected value of x. So it's going to converge, and it's going to converge to the true mean. All right, so this, how do we prove this? And I think it's worth just looking at this because, again, in sort of the way that I was saying before, that RL is both shallow and deep in terms of its mathematical background. On the one hand, a lot of these things were invented from people with deep intuition about RL processes. On the other hand, there's an extremely deep literature from stochastic approximation, et cetera, that gives us nice results in terms of when these things are sound and what are the conditions we need. Typically, we're going to end up calling this the learning rate. And it also has implications for when we start to think about function approximation. And so I think thinking about where these conditions on the learning rate come from in order to ensure convergence is helpful. So why does this work? Okay, so what we're going to say is that by the independence assumption, for m greater than or equal to 0, remember m is just indexing our estimate, we're going to have the variance of our estimator is going to be equal to 1 minus alpha m squared, the variance of our previous estimator, plus alpha squared m, the variance of our variable. Okay. Alpha is less than 1, so this is going to be less than or equal to 1 minus alpha m, where I've dropped the squared, variance of um plus alpha squared m. Okay, because I've assumed all of these are bounded between 0 and 1. All right, so we know that alpha m has to be going to 0 because this sum has to be less than infinity. So alpha m has to be going to 0 eventually. Okay, and we're going to assume, we're going to define epsilon being greater than 0, so some epsilon. And we're going to assume, this is going to be a proof by contradiction. We're going to assume that there exists an n such that for all m, so for all future updates after that, the variance of our estimator is large. Okay. So what is this saying? This is saying at some point we're going to reach a point at which our variance is still large and it's not decreasing. So remember, what we want to do is we want to show that this is going to the true estimate. Okay. So what would this imply? This would imply that the variance of our estimator, which is less than or equal to the variance of the previous estimator, minus alpha m epsilon. Okay, because we have this minus alpha m epsilon, we're saying that its variance is at least epsilon, so I'm just plugging that in for the variance there. So 1 times this minus alpha times this, plugging this in as a lower bound. Okay. Plus alpha squared m. Okay. And this we know. So then we're going to rewrite this. This is just for one step. So let's think about continuing to do this for many steps. So we're going to have mu m plus n. This is going to be less than or equal to variance of mu n. So I'm just continuing to go more time steps out from this equation. Minus epsilon sum over n equal to n to m plus n. So these are just a number of time steps after we've assumed that the variance is large. Okay. Times alpha n plus sum over n equals n, m plus n, alpha squared. Okay. But I've assumed that this sum is going to infinity. Okay, so the square is is less than infinity, but this is going to infinity, which means that this is going to infinity. Minus epsilon times something that's going to infinity means that this is less than or equal to minus infinity. So eventually it will have to be smaller than epsilon. So that's a contradiction. Okay. So this can't be the case. So, which implies that at some point, sorry, I know this is a little bit low for some people. So this implies that there has to exist an n such that for all m0 greater than or equal to n, the variance is small. The variance of our estimator is small, is less than epsilon. So at some point our variance has to start getting super small. And then what we can do in that case is we can choose n, choose n large. Can anybody see that or no? All right, maybe I'll just write it here. Let's see if we can do that. Okay, this might be better. Okay, so what we're going to do is we're going to choose n large enough such that for all m greater than or equal to n, alpha m is less than or equal to epsilon. Remember again, alpha m is getting smaller and smaller, so at some point it will be smaller than epsilon, so that's okay. And so at that point, the variance of u m plus 1 is less than or equal to 1 minus alpha m0 epsilon plus epsilon alpha m0, which is equal to epsilon, which means that mu m is less than or equal to epsilon for all m greater than or equal to m0, which means that we're going to converge. So the reason that I thought it was useful to go through all of that is that basically tells us something about why we're going to pick particular learning rates here. It's saying that if we pick learning rates such that if we sum them up, they go to infinity. If we sum up their squares, they go to 0. Then we're going to be guaranteed that this is going to converge to the true value function of pi by doing this TD approximation. Yeah?
Just by the quantifiers here, do we want to do something like for all epsilon, then there's, so our ultimate conclusion should be something?
Yeah, so you can pick epsilon you can make epsilon anything here. That's right. Yeah, so this is for any arbitrary epsilon we want to pick, and so eventually we're going to be think this is. I'm going to erase that there. This here. We can pick epsilon to be anything we want, and so we can make the variance of epsilon to be going to 0 here. So eventually our estimator is going to converge asymptotically to the true mean function here. This is going to go almost surely to the expectation. Okay, so that basically wraps up policy evaluation. And what we've seen here is we've seen policy evaluation where we use Monte Carlo, which is high variance but unbiased. We've seen TD where we do potentially high bias but lower variance. And we've seen some indication that it can be sound. Now, I also wanted to do this, and I know that this is going a little bit into the weeds and is not directly connected to this immediately, but I also wanted to highlight where the subtleties start to come in. So the algorithms themselves are very, very simple, but making sure that we prove that they are asymptotically consistent is not, and ends up starting to have deep connections to stochastic approximation. Okay, yeah?
You can just apply this theorem immediately to the what we saw before for the temporal difference and as is?
No.
No?
No, there's some other things we're going to want to think about in terms of this, because these are not IID estimates. Because they're functions of previous. Okay. So there's a lot of complication. Like there's several additional complications, which is why I was, but I wanted to illustrate where some of those complications start to come in. So there's multiple complications. One is that, how do we even pick what this alpha update is, and how could we be sure that this would converge? This gives us a sense of the type of techniques we'll need to show that it converges, and under what guarantees. But one needs to do a little bit more work on top of this. That result does not directly apply. Yeah?
So you would run this algorithm in all states, but then I guess you're not, like the v hats, can you index them by iteration of the algorithm? Because then it's not clear to me if the v hat inside is coming from this current iteration of the algorithm, or is it coming from the previous iteration of the algorithm? Because I may have updated it for one state, and then am I using the new update, or am I using the old?
You generally, great question in terms of what will the actual algorithm be. So basically you'll always be, you can think of this as doing like a line of code. So we're going to be, if this is a vector, we're going to be plugging in our from our previous vector of value function.
So the v hat s prime that's inside is from the previous vector, it's not from the new update.
Yeah,
Okay.
these are from our previous vector. So we compute all of this, and then we'd reassign this. We're doing this incrementally. So you can think of doing a for loop over every time I'm in a state, then I take an action toward s prime, I do this update. Then I update my state to update my s prime becomes my s, and I take another action. Yeah.
Minus goes to 0 as our estimate becomes more accurate.
Yes. So asymptotically, it's consistent. Good question. Okay. This is all for the tabular case. So we haven't talked at all about if we're approximating this with functions. Yeah.
This is policy evaluation, right?
Only policy evaluation. Yes. Okay. This is only policy evaluation. What I will do, I think mostly we'll just talk about it next time. Let me just briefly say some properties. Okay. So which is, we can't directly use this when we don't have models of the domain unless we start to get empirical estimates. TD can be used in the infinite horizon case. It requires Markovian structure. This does not require Markovian structure. And I think those are most of the critical properties, I would say. And they all converge to the true value in the limit under minor assumptions about our learning rates.
I mean, I understand the computation depends on the size of the S and A spaces, but does the convergence rate, does that influence fine?
Good question. Does the convergence rate matter? So yeah, computationally it matters in terms of, I don't think so. I should double check that. I'll check that before tomorrow. I don't think the convergence rate is affected by the state in the action space here. Certainly for this it shouldn't be, except for your initial starting state distribution, like the question that was asked before. If you have a distribution over states, you're going to be, the amount of data you need is going to determine by what's the minimum probability of sampling any of those states. Okay, so what we'll talk about tomorrow is an extension of this. I'll just give a brief highlight of where we're going. So what you can see here is we're updating the value for a particular policy, but you could imagine doing something extremely similar if you were trying to get an approximation to the value function where instead of plugging in the next state for the policy you have, you insert a max here. So if you had a Q value here instead, which we do not, but if you had a Q value, then you could imagine putting a max over A for the next state. And that's going to give us some way to start doing control. So what we're going to be talking about next is that in the control setting, now we've got a good set of tools for trying to do evaluation. And now what we're going to do is try to figure out how we should actually be gathering data in order to both compute V star and pi star. And the conditions that we're going to need are going to be pretty similar in terms of things like learning rates. But as has been highlighted by several of you, we're going to need conditions over exploration, which is how we're sampling state action pairs. And just again, for a little bit of intuition of that, the intuition is that if we have sort of a policy we're following, a little bit like the policy improvement case, so you can imagine doing some amount of policy evaluation and then you do improvement. If we don't sample some state action pairs that don't happen to look good under our current policy, we won't get any data about them. And so in order to have convergence, we're going to need to be able to try all of the state action pairs a little bit, at least, unless we're making sort of assumptions about generalization. And so we're going to start to get into that next time to talk about like how should we do that sampling. Yeah.
Why the variance convergence implies the almost sure convergence?
I didn't go into it. Yeah, so I didn't. I did not go through the last few details of this. I'm happy to talk about it offline. Yes.
I think the L2 convergence does not imply monotonic convergence.
Yes, I'm happy to talk about. So it's a great question. Yeah, this is basically showing L2 convergence, and then I didn't step through the additional details we need. But great question. Any other questions? All right. See you tomorrow.